Start by fixing some errors. Last time I was talking about triple helix DNA. I accidentally said Wolfgang Pauli. We will talk about Wolfgang Pauli, but it was supposed to be Linus Pauling. Okay? That's mistake number one. The other thing that Ekin mentioned is the only particle that has spin 0 is Higgs boson, apparently. And we can start with the new topic. Okay? So, what is the new topic? I can erase this. The new topic is identical particles. Okay, so it is every now and then in thermodynamics you get a hint of what's coming next in quantum mechanics, right? So, for example, Boltzmann wanted to discretize the phase space, right? And it is now discretized thanks to uncertainty principle. Then there is also this identical particles problem in statistical mechanics, right? If you don't take it as identical particles, some calculations don't work out. So, with that brief introduction, let me just jump into this operator, P. Particle exchange operator. So what is it? Why you are far away from me, as far as possible? Okay. So particle exchange operator does the following to the wave function. If you operate on the wave function with particle exchange, guess what? It exchanges the particle coordinates. So first particle becomes the second particle becomes the first, right? Now if you do it twice, p squared, what happens? It comes back to itself, right? So far, how are we doing? Good. It seems like this is an eigenvalue equation, operator times wave function, right? And then there is this value times the wave function. And it seems like this is 1, and p can take two values. It can be either plus 1 or minus 1, because p squared is 1. So far, are you with me? Yes? Turns out that these are fundamental things. If you have a pair of bosons, then it's plus 1. If you have a pair of fermions, you have minus 1. What does it mean? It means that, let me just copy this. There are two types of particles. Bosons under exchange of coordinates, their wave function would go to the same value. So their wave function needs to be symmetric. And fermions, for fermions, it needs to be anti-symmetric. Okay? So we call this one symmetric. Let me write it down, here. This is symmetric. and this is antisymmetric. It just so happens, for deep reasons, is that bosons have full integer spins, like Higgs boson is 0, or like photon, which is 1, right? They are bosons. And electrons, neutrons, and protons are fermions. They have half integer spin. Okay? So far, do you have a question? Any question at all?
Yeah, I have
yes.
What if there's 3 positions in the wave function?
Very good question. What if there are 3 particles, right? Very good question. Then the wave function, so there are 3 electrons, for example, right? Then the wave function needs to be antisymmetric with respect to each particle exchange. So whether you change 1 to 2, 1 to 3, or 2 to 3, for each one of them, it needs to be antisymmetric. Okay? Okay. So then, let's now talk about many-body wave function. Let's go back to many-body wave function. Many-body wave function, including spin. Here we are writing many-body wave function, just the space part. But the full many-body wave function has also the spin part. So for a 2-particle, you can write it down like this. And I'm going to extremely simplify stuff, okay? Otherwise, it's hard to understand it at all, okay? So here's the simplification that I'm doing. I'm going to represent it. So what do you have here? I'm going to represent this part as a coordinate. For example, it could be between 0 and a. It's a continuous coordinate between 0 and a. This is also going to be a continuous coordinate between 0 and a. So we are going to talk about 2 particles in a box. Okay? There was 1 particle in a box. Now there are 2 electrons in a box. This is going to have only -1/2 and +1/2, or I will just represent it with either up or down. And this one also will be represented by either up or down. Okay? So what does it mean? So let's talk about 2 electrons in a box. 2 electrons in a box. Let's spend some time on making a nice plot, okay? Then we are going to use it a lot, so let's say this is spin 1, this is spin 2, and it can be down or it can be up. And let's say this is down, the S2 can be down or up. Do you have any questions so far? No? Then, okay, sorry. I will come back to this plot, okay? I will come back. This is not going anywhere. This is here. Let me first talk about the space part. The space part. So if I have an electron in a box, we were talking about a wave function like this, right? Single particle. For example, if it's in a box, it would be like this. Or it could be like that, right? So it's one coordinate and we can plot it like this. What about psi of x1, x2? How would you represent that in a plot? You need two coordinates, right? You need x1 and you need x2. Please don't get it wrong. It's not one particle in a two-dimensional box. It's two particles in one-dimensional box. Do you follow this? Yes? So, it's going to be some function, some two-dimensional function, but it doesn't mean that it's in a two-dimensional box. It's in a one-dimensional box. Just the many-body wave function has now two dimensions. All right, very good. So how can you build a symmetric function? Let me talk about symmetric function, symmetric space function. So let me show you something. This is a box, and this is phi 1 of x. Do you agree? Just one particle. And this is phi 2x. Phi 2x. Now I want to construct phi x1, x2, which is phi 1 x1 multiplied by phi 1, look, phi 1 x2. So the indices are really important here, so please follow them, and if I make a mistake, you correct me. Do you see that this is also 1, this is also 1? Do you see it? This wave function is symmetric. Why it is symmetric? Because if I replace x2 and x1, I get phi 1 x2 times phi 1 x1. Do you see it? Is it equal to each other? So it's symmetric. These are, so you can, if you do phi 1 times phi 1, phi 1 x1 and phi 1 x2, you construct a symmetric wave function. How are we doing so far? Let me show you in a code. Okay. So look at this. Let me just ignore these parts. Look at only here. Do you see? Sine of pi x is your phi 1. Sine of pi x is phi 1. And as you can see, there is sine of pi x1 and sine of pi x2. Is this wave function symmetric? Yes, right? So let me plot it. I can plot it in different ways. So for example, I can plot it as a mesh, or I can plot it as like this. Doesn't matter. Just we will be seeing it from above. So let's run this. So seeing it from above, it looks like this. Okay. From the sides, it looks like this. Are you happy? Any questions? No? Good. So for example, if I had phi x1 x2 equals to phi 1 x1 phi 2 x2, Would it be symmetric? No. Would it be anti-symmetric? No. Because phi x2, x1 is not equal to phi x1, not even the minus, not even in the minus way, because this one basically is phi 1 x2 and phi 2 x1. So there's no way to get them equal to each other. Let me show you how they would look like. So is it okay if we continue with image only? So for example, f1 is this one. Let's write f2, which is, so I'm going to add 2 pi x2, if it's okay with you. Do you understand it? Yes? And then there's f3, which is x2 first, x1 next. Are you following? And then I'm going to draw this one, f2, and then I'm going to draw f3. Okay? So look at this. This looks like that, that looks like this. Okay? And there's no way to make them equal to each other, right? So these are nice representations. How, so far we have stumbled upon a symmetric wave function, right? Can we build an anti-symmetric wave function? Yes, we can. What does anti-symmetric mean in general? So let me show you something. The symmetric one was looking like this, right? Okay. The symmetric one looked like this, right? And its symmetricity, let me call it that way, can be seen when you replace, okay. Sorry. Sometimes I don't find the right words. So, if you have a wave function that you can flip over the diagonal and it turns back to itself, then it's a symmetric wave function, right? Now, the other two functions that we have seen today, one of them looked like this, and the other one is 90 degrees rotated, right? And we can see why they are not symmetric. Am I going too slow? Yes? No? Okay. So do you see that if you flip along the diagonal, they don't map back to themselves, right? So what kind of a wave function would map to itself with a negative sign? This kind of a wave function. So let me just note that these are neither symmetric nor asymmetric. But this one, if I construct something like this, then it is going to be anti-symmetric. Because if I flip over the diagonal, it maps exactly back to itself with the negative sign, right? This is anti-symmetric. Do you have any, do you have any suggestion how I can achieve this kind of a wave function?
Parameter should be the multiplication of tools.
Parameter should be the... Go back to quantum mechanics. How would you construct an antisymmetric wave function?
I will add -1 to the power of blah blah blah.
Okay. I think you forgot. Which is totally fine. So what you do is the following.
Like, I will, like, psi1, psi2, minus psi2.
Exactly. Exactly. So what you would do is phi 1, x1, phi 2, x2 minus phi 2, x1, phi 1, x2. Did you follow this? Now, if I replace x2 with x1, what do I get? I get phi 1, x2, phi 2, x1 minus phi 2, x2, phi 1, x1. Isn't that the negative of the above? Yes? Do you see it algebraically? Because this one is negative of that one, and this one is negative of that one. Yes? So if you draw this, let's draw this. Let's have an F4. F4 is this one. F4 is F2 minus F3. Do you agree? Was it too sudden? Maybe it was too sudden. Let me show you. Let me draw also F4. Do you see it? Well, this seems to be not working. Because I'm drawing axis, not me. And the MATLAB is drawing axis weirdly. Set GCA y direction. What was the thing here? Anyone?
No.
Normal? Fingers crossed. Yes. So normally MATLAB draws this y-axis abnormally. Now it's drawing from bottom to the up. Are you with me? So at the end of the day, this is what we get, and this is exactly what we were looking for, right? And along the diagonal, it's flipped. So far, how are we doing? Naz first.
Should it be this diagonal? I mean, it can't be the other diagonal?
No, because when you are flipping particles, when you are exchanging particles, x1 and x2, what you are doing is you are flipping these two coordinates, right?
Okay.
So they are like this, and you are flipping those two coordinates. Yes? Good. Now that you got, yeah, you had also a question.
For the shape in the middle,
In the middle.
yeah, if you flip that shape around the, a diagonal, what shape will it be?
You will get the shape on the left.
Okay, so it's symmetric.
No, it's not itself. It's something else. Right? If you flip this one, it goes to a different function. And if you flip that function, it goes back to this function. So we need to have one function having a symmetry, not two functions.
Different.
Right? Are you with me, or?
Yeah, but the shapes are symmetric around the diagonal, but the functions are different.
These shapes, so if I erase one of them, Let me erase this one. Okay? This shape by itself is not symmetric with respect to diagonal, isn't it? Because if you flip with respect to diagonal, then the sine 2 pi x goes from being on the y direction to the x direction, right? Very good. But this by itself, this other one by itself, this one by itself can be flipped along this side, and it will map to itself with a negative sign. Yes? Very good. Now, let me think just a little bit. But what we want to achieve is not just in space. We want to achieve antisymmetricity both in space and spin. I mean, we want this one to be antisymmetric. We want this one to be minus phi x2, x1, s2, s1. Does it make sense? Yes? This is what we are searching for electrons. Okay? Because they are fermions. Let me draw that one. The way that I draw this four-dimensional thing is to put plots within plots. It's like Inception, okay? So I have an outer plot which is for spins, and inside that plot I have an inner plot which is for space. So each quadrant here has its own x1 and x2. x1 and x2. Do you see it? So let me draw you an antisymmetric wave function that is antisymmetric when you include the spins and space all together. Okay, here it goes. I have a plus over here and a minus over here, and 0 over here. So let me draw it with black. Is this antisymmetric with respect to particle exchange or not? Just imagine flipping the whole thing along this diagonal. Then you not only flip S1s and S2s, but you also flip X1s and X2s. Do you see it? Yes?
Can you explain once more how did you draw the shapes?
I will come back to the shapes, but do you agree that that's the next question? How did I draw the shapes? Okay, that's exactly the question. But just flipping wise, do you agree that if you flip it, red goes to blue, blue goes to red, and they are negative of each other, and this makes sense? So, what is this wave function, right? What it corresponds to? Remember, this by itself was phi 1 x1, phi 2 x2. Do you remember that? Yes? And this one by itself is minus phi 1 x1, phi 2 x2. Right? Not phi 2. You shouldn't say yes. Be careful, please. It's phi 1 because it has one hump on both sides, right? Are you following? Now, What is this? This is phi 1, phi 1, phi 1 x1, phi 1 x2 multiplied by up, down, no, multiplied by down, up, why down, up? Because of this down and this up. Yes? Plus minus phi 1 x1, phi 1 x2 multiplied by up, down. Yes? So what do you have in total? You have phi 1 x1 multiplied by phi 1 x2 multiplied by down, up minus up, down. Yes? So this wave function is antisymmetric. It has symmetric spin part, space part, symmetric space, and antisymmetric spin part. But if you have symmetric multiplied by symmetric, then you get symmetric. Symmetric multiplied by antisymmetric, antisymmetric. How about antisymmetric, antisymmetric? Symmetric. Okay. Good. Do you still have a question on this part? So we have found a wave function that is symmetric in space and antisymmetric in spin. Can we find a wave function that is symmetric in spin and antisymmetric in space? Yes, we can. Then the whole thing is not antisymmetric. I love technology. Do you see my point? The whole thing will not be antisymmetric if we rotate the whole thing. The way to achieve this, I will show you one way. So remember, we want to be antisymmetric with respect to this. Here is an offer. And 0 everywhere else. How about this? Is it antisymmetric in total? Yes? So let's construct this wave function. What is this? Do you remember? It was phi 1 x1, phi 2 x2 minus phi 1 x2, phi 2 x1. That's the space part. And the spin part is easy for this one. The spin part is just simply up times up. Up, up. That's the whole wave function. Or down, down. We can also go with down, down. That's another shape. Right? We can also have down, down. Let's draw down, down.
Can we also go up, down, plus, down?
Yes, we can. copy, paste. Is it boring? No? Are you sure? So I'm drawing this one for completeness, really. So I can have over here, and I can have over here, and that will give me this expression with down, down. Copy, paste. Notice that these two wave functions, in both cases, space part is anti-symmetric. So I have anti-symmetric space and symmetric spin. Same here, same at the bottom. So I can just copy this one and paste it here. Right? Are you happy? Why you are so happy? You are a bit too happy. You haven't looked at it this way.
A few minutes ago, I thought I understood, but now I realized it. Now I understand.
Brilliant.
I hope so.
Brilliant, brilliant. It will go on forever with everything. Yes. Okay.
When we say zero, it means that there is nothing in. Okay.
So it's just down, down spin state. But then again, I'm simplifying things, okay, a lot. I'm building towards just, I'm going to say one word at the end, like 2 words at the end, and I'm doing all this for those 2 words so that you understand it. Coming soon. So let me, there is one more wave function that can be drawn, which has anti-symmetric space and symmetric spin. So we have, okay, let me show you. We have this one being here, we have this one being here, or we can put both of them here, right? But they have to be in the same direction. So the last one is this one. Yes? What is this one?
Both of them are
Hmm?
symmetric. It's anti-symmetric in both space and spin.
No, it's symmetric in spin. Let me show you how. It's still symmetric in spin because what do we have here? Can I gather my thoughts? Yes, I can. Phi 1 x1, phi 2 x2. Let me write it down so that it fits because it's a bit longer than the other ones. So I'm going to copy this part, which is the same. But in the spin part, you have down, up, right? Down, up, plus. Do you see? This wave function and this wave function are the same. So it's a plus. That's why it's symmetric. Plus, up, down. So it's still anti-symmetric in space and symmetric in spin. Copy, paste. Okay? What I didn't take into account is normalization. Let me just quick.
Can I ask you a question?
Sure.
If you change the, in the right bottom part, up down section, the red and the blue one with each other, if you change them, so we will reach at anti-symmetry in an anti-symmetry space.
Yeah, that's what I think at first.
No, it doesn't, because let's forget about space. Just do spin. Only spin. Isn't it symmetric? It's plus, it's not minus.
No, not at that one.
Ah, the first one.
No. The last one. Yeah, in that shape, in the up-down, plot, up-down plot. The right bottom one. If you change the red and the blue,
But you are not allowed to do that. You are not allowed to only change spin. You are changing particles. So the only operation you are allowed to do is to flip the whole picture with respect to diagonal. You are not allowed to flip only spins. You also have to flip. You also have to flip the space part. Does it make sense? No? Let me explain to you. So this is S1, but these are X1. So when you are switching 1 with 2, not only S1 goes over here, becoming S1, but also X1 is flipping over here. Yes? So the whole thing flips. You don't like it?
Okay.
Yes.
What about pi x2, pi to x1?
Phi 1 x2, phi 2 x1.
Minus pi 1 x1.
Okay. This is just negative of the other one. Right?
How about the spin? Spin is same or different?
Spin, so so far you have written an anti-symmetric space, right? This needs to be accompanied by a symmetric spin for the whole wave function to be anti-symmetric, right? As you can see, we have arrived at that keyword. As you can see, there is only one state with anti-symmetric spin, while there are 3 states with symmetric spin. Do you know how they are called? Okay, let me tell you. This one, no, the whole thing. This one is called singlet. Okay, I didn't like this. This whole thing is a singlet state. And these 3 things, 1, 2, and 3, they are together form the triplet state. Okay? You must have heard of it before. Even if you are doing chemistry, like there is this singlet oxygen which is very reactive and stuff like that. Yes? Huh?
There are duplets and octets.
No, that's a different
They
thing.
have the same logic, right?
Let's see. So, how are we doing with time? We have 3 more minutes. Any questions? Let me just fix the normalization and then we give a break. We have a break. So, when you are writing wave functions like this, you have to add 1 over square root 2 at the end so that it's normalized, right? So it appears everywhere here, 1 over square root 2, here also 1 over square root 2, here also 1 over square root 2. Here we need 2 1 over square root 2, so we have 1 over 2. Because we need 1 over square root 2 both for the space part and for the spin part. So the whole thing is 1 over 2. Okay? Do you have any questions? It is not complicated, come on. I have drawn you pictures. What is complicated? It is, okay, it is complicated. Okay, I agree with you. But now you have learned, we will talk about it after the break, but you have energy levels in particle in a box, right? If you didn't have this course today, if I asked you put 2 electrons into this system, you would put it here, right? Like this. Yes? Because that's how you are used to doing it with atomic physics and stuff like that. Now you know what you are doing. What you are doing is you are creating a singlet state. Okay? If you put it like this, then this is a triplet state. By the way, there is a confusion here, because once we draw it like this, we usually represent this one singlet state like this and triplet state like this. But be aware that triplet state has 3 possibilities within it. Although we show it with up, up, what it really means is it's up, up, down, down, and up, up, plus down, up. Up, down, plus down, up. Those 3 things are there, but when they are writing up, down, it means up, down, minus down, up. So this means only one thing in chemistry books, etc. This means 3 things at the same time. That's why one is called triplet state, the other one is called singlet state. Okay, let's have a break.